Today I'm going to present my paper DeepServe, Serverless Large Language Model Serving at Scale. And this is a deployed system paper, so my presentation will focus on somehow different. I'm mainly focused on our design thoughts and findings when building the system and put it online. So this paper actually introduced part of our system XDS, which stands for extremely disaggregated system. And actually, the XDS is the serverless AI platform for the Huawei cloud. It unifies all the AI workloads like LLM inference, post-training, and agent serving on a unified resource pool, and to achieve both good performance and good cost efficiency. And this paper only focuses on the LLM serving part. We call it DeepServe. And another background is that we are building on Huawei's own accelerators, Ascent neural processing unit. And this is a figure, the right side is a figure of the latency NPU, which has 2 dice on the chip. Each chip has around maybe 25 to 30 AI cores, and each AI core has one node, a few cube cores and vector cores. And there is also an ARM CPU on the die. And on the left side, it is our Cloud Matrix SuperPod. In the current version of the SuperPod, we have 48 nodes, totaling 384 NPUs in the SuperPod. NPUs within the SuperPod are interconnected with ultra-high bandwidth, low latency interconnections, which is about 200 gigabytes per second, and the interconnection is equipped with low store semantics. And NPUs across different SuperPods, they are connected with a Rocky network which can scale out. And the Rocky network has not as good as latency and throughput as the intra SuperPod connections. And we also have the VPC network to connect the CPUs. So let's come back to our paper. This paper mainly focuses on 3 challenges. First, the LLM model is getting larger and larger, like the MOE models is very large, so the inference engine is transformed from a single node software into a distributed system. And also the LLM inference is becoming stateful due to the KV cache reuse. So the first challenge is how do we build an inference engine to tackle this challenge? Second is that how do we schedule the workloads in the whole large-scale distributed system? And the third one is that because the third one is that how do we handle the dynamic scaling of the model due to on the large-scale cluster? So the talk will have 4 components. First, I will go through our architecture and our serverless abstraction to unify all the AI workloads. And the second part will be our FlowServe disaggregated serving engine. And third one will be brief, it's about request scheduling. And the fourth one is about how do we scale out fast about the LLM engine. And at the very last, I will also share some of our recent progress in the past half year, as this area is really evolving really fast. So I will first show our overall design with 4 major design goals. The first one is that, and the most important design part is that we wanted the system architecture and the abstraction to be as simple as possible so that it can be comprehended by everyone. In the industry, we found that some of our developers, they are not system engineers. They may have a diverse background. Some of them are algorithm developers. Some of them are from big data areas. So we want the system design to be very simple and easy to understand. And second, since the AI workload is rapidly expanding, we need to ensure that the whole system has no single point of bottleneck. Each layer of the system can scale out independently. And third, we need to think the inference will get more and more disaggregated due to the introduction of SuperPods. So from a single engine to the current PD disaggregation. And we are also working on disaggregating the attention and MOE layers to different cars in the single SuperPod. And fourth, I put it to last because it is not closely connected to this paper, but it is also very important. We see that LLM serving workloads have strong diurnal workload fluctuation pattern. And we see that actually the load will drop significantly even at the lunchtime. So we need to have other workloads like post-training, agent serving to consume the results at the valid time. So this abstraction need to unify, consolidate all the AI workloads and scheduling them on a shared results pool. So this is our, I will go through our architecture. At the top layer, we have a front end. It provides standard API, and it also involves a flow control and authentication. And the second layer is what we call job layer. For the LLM serving, a chat request is a job. And for other requests like fine-tuning, a job can have multiple jobs. A request can have multiple jobs. And a job can also spawn multiple tasks to execute, and each job is executed by a corresponding type of job executor. The job executor is horizontally scalable, and it knows the down layer, lower layer task executors, and it orchestrates the task, schedule each task to the corresponding task executors. And the lower layer is the task executor and task layer. The task is the smallest unit of work, and task executor is the smallest scaling unit. For instance, in a PD disaggregated serving, a preview instance is a kind of a task executor. And we have TEs with the same properties, like TEs with the same base model, TE with the base TP parallelism, and TE with the preview or decode role. They form a TE group. Note that because we want to an engine to serve multi-LoRa inference, so LoRa is not a property. It is like a attribute added to a TE type. And we also have a relational tensor cache, which is the unified data plane across all the TEs to manage the KV caches. And it handles PD, KV transfer, KV reuse, etc. I will go through it in the future. And we also have a cluster management. It handles the service discovery, it handles the failure handling, and a very important part is harm detection. We find sometimes the LLM inference does not crash, it just hung there. And we need to know that the request get into the inference engine, but it does not get out. So we need to kill it intentionally to recover. And the cluster management also handles the gun scheduling. One of the important things is that as the serving instance, like a large MOE decode instance is getting very large, sometimes we need to intentionally queue some other instance to accommodate such a large instance if we want to scale out a MOE EP inference engine. So the next part is about our FlowServe disaggregated serving engine. The design principles have we must ensure that we have extreme performance. It is very fast, and we also want it fast evolving so that we can test and implement different kinds of high-level optimization onto top of the serving engine. So we have three design principles. The first one, we have like a microkernel inspired design. We decouple the serving engine from a single software into different modular components, and if each of the components can scale independently. And the second part is NPU-centric execution. Our goal is that we keep the NPU busy. We do not want NPU to wait for other resources such as CPU preparing the inputs, such as DRAM, such as storage. And the last one is that we have a simple SPMD design. Actually, this is a common sense for all the LLM serving engines like VLM, Gengyuan. And another thing I want to share is that actually we had a heated discussion on the programming language selection. At the end, we choose to use both Python and C++. Python is very important because it facilitates rapid iteration. It is friendly to algorithm engineers, but Python is notoriously slow, and it is hard to tune the performance. Sometimes we use the asynchronous I/O. Sometimes we use the coroutine, but the coroutine is never scheduled in the Python interpreter. So for the performance critical part, we rewrite it into C++, like the data plane. For the KV transfer to the KV swap, we use the C++ dynamic library to implement it. So this is the FlowServe, our inference engine. At the very top is the TE shell. This is a shell, and actually changed our FlowServe from an engine into a TE in the cluster. And we have a tokenizer and the detokenizer. This is actually also a standalone process. It can independently scale, and it understands client-side APIs, like what is reasoning contents, what is tool cost, and it also provides shortcut to the front end during the streaming response. And we have a SPMD pattern, and we let the master to always schedule one step ahead to avoid accelerating. I will have a figure to show this. And we have the relational tensor cache, which is the unified data plane to manage all the tensors, not only the HBM blocks but also manage the swapping between the HBM to the DRAM, the tiered memory to the SSD, and we also have the data transfer from prefill to decode to prefill, and we have the cross TE or cross engine capability use. We have this kind of unified data plane to manage all the data, and it also provides a synchronous API with cost model, so that we can determine whether to reuse the KV cache or we just recompute it. And we use a synchronous API so that the NPU do not need to wait for the swap. It can go ahead and use the KV cache in the next loop. And this is what we call a fully asynchronous workflow. The upper part shows when we are doing the KV cache reuse. When requests come, we first go to the RTC index to see whether we have some KV cache to reuse. And we have a cost model to determine whether it is efficient to reuse the KV cache or to recalculate it. And we use a asynchronous disflow, which is a C++ thread to populate the KV cache. And for the scheduling, we see that we have a synchronous schedule. When we are calculating the I loop, we schedule for the next part, which means actually the NPU can continue to calculation without waiting. But that means the stop checking is late. Sometimes we may have one more tokens back after the US, and so the system needs to just cut it and make the token after the US does not show to the clients. So this is our performance, and see that we have different versions, and after each optimization, we have a better performance. Details can be found in the paper. And the request scheduling, due to time limit, I will go faster. We have 3 design factors. The first one is prefix caching, and we think it is a top priority because skipping computation is always the most effective way. And the second is that when the client requests come, we must determine whether we want it to be PD disaggregated or PD co-located. And we do some tests. We found there is no clean winner. Sometimes if the prefill or decode length changes, the design choice will change. And the third one is the current load of each TE. And another findings we found, sometimes we want skewed distribution. We do not want the request to be perfectly balanced, because such a way will facilitate resource reclamation. And the fourth component is the fast scaling. We have 5 steps to scale out. First, we need to prepare the pods, the environments, and the second step, we need to preload. We call it preload phase. We need to init the engine, like the NPU context, the Python libraries. Loading the Python libraries can be very, very slow, and we need to set up the group communication. The first 2 steps can take more than 10 minutes sometimes. So we use pre-warm to have a pre-warm tool for the pods and TEs so that we can skip this part when we are scaling out. And we also have another 3 steps is loading the model onto TPU, onto the NPU, and we also need to warm up the engine and announce the TEs to the cluster. For the model loading, we have 2 paths. The first one is from DRAM to SSD. We also co-design it with the pre-warm tool so that we can, most of the time, load from the DRAM. And we also have an NPU fork. We use the high-speed device-to-device links to scale out. And this is the breakdown. Okay, the last part is the progress after our paper submission, because it has been almost half year. So we are evolving from a inference engine to a supernode native architecture. We maybe take the DeepSeek R1, which is a very large MOE model as an example. We have a fully disaggregated inference engine. We have an omni request scheduler, which means we have one level of schedule for a multi-DP inference. And we have like XCCL, which is a memory semantic-based library for the superpod. And we have a more better reliability. Sometimes we have some errors. We can use a recomputation, like a try-catch finalize, instead of just crash. And our peak sustained throughput can achieve like 2,300 tokens per MPU at the TPOT of 50 milliseconds. And we have a comprehensive technical report, and we are preparing it. It will be released soon. So this is the end of my presentation. I would like to take questions.